In the vast, silent theater of the cosmos, an invisible force orchestrates the grand dance of celestial bodies. It is the fundamental architect of everything we see, from the smallest dust motes to the most colossal galaxies. This ubiquitous presence, often taken for granted, is gravity, the unseen hand that shapes the universe. Gravity is more than just the reason an apple falls from a tree. It dictates the orbits of planets, ignites the furnaces of stars, and sculpts the immense structures of galaxy clusters. Without its ceaseless pull, the universe as we know it simply would not exist, adrift in an eternal, formless void. For millennia, humanity observed the sky, charting the movements of stars and planets, yet the underlying mechanism remained a profound mystery. Ancient civilizations developed complex cosmologies, but none fully grasped the unifying force that bound their observations together. It wasn't until the scientific revolution that a cohesive understanding began to emerge. Visionaries began to apply mathematical rigor to observations, slowly unraveling the secrets of the cosmos and laying the groundwork for our modern understanding of this fundamental force. The story of gravity's discovery is inextricably linked with one of history's greatest scientific minds, Isaac Newton. Living in the 17th century, a time of intellectual ferment, Newton sought to explain the universal principles governing both earthly and celestial motion. Legend has it that a falling apple sparked Newton's profound insight, leading him to ponder why objects always fall towards the Earth's center. This simple observation led to a revolutionary concept. The same force that pulls an apple to the ground also holds the moon in its orbit around Earth. In 1687, Newton published his groundbreaking work, Philosophiae Naturalis Principia Mathematica, or Principia, which meticulously detailed his law of universal gravitation. This monumental treatise laid the very foundation for classical mechanics and astronomy. Newton proposed that every particle of matter in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This was a radical idea for its time. Newton's law allowed for the precise calculation of planetary orbits, predicted the existence of previously unseen celestial bodies, and offered a logical, mathematical framework for understanding the mechanics of the solar system. It was a triumph of human reason. However, Newton's law described gravity as an instantaneous action at a distance without explaining how it worked. It was a description of the what, not the why. For centuries, this remained a perplexing mystery, a mere mathematical description of an unknown mechanism. Despite its descriptive power, Newton's classical gravity faced challenges. It couldn't fully explain certain phenomena, such as the anomalous precession of Mercury's orbit, tiny deviations that hinted at a deeper, more complex reality underlying gravity. The stage was set for a new paradigm, a revolution in physics that would completely redefine our understanding of gravity and the very fabric of the cosmos. This revolution would come from one of the 20th century's most iconic figures, Albert Einstein. In 1905, Einstein introduced his special theory of relativity, dramatically altering our concepts of space and time. It posited that the laws of physics are the same for all non-accelerating observers, and the speed of light in a vacuum is constant for all. Special relativity showed that space and time are not independent entities, but are interwoven into a single continuum, space-time. This profound realization paved the way for Einstein's even more revolutionary theory, which addressed the nature of gravity itself. A decade later, in 1915, Einstein unveiled his general theory of relativity. This theory wasn't just an improvement on Newton's ideas. It provided a fundamentally different understanding of gravity. It wasn't a force acting at a distance, but a manifestation of geometry. Einstein proposed that massive objects, like stars and planets, warp the fabric of spacetime around them. This curvature then dictates the paths of other objects, including light, causing them to fall towards the massive object, much like a marble rolling into a dip on a stretched rubber sheet. This revolutionary concept explained not only why objects fall, but also why celestial bodies orbit each other. They aren't pulled by an invisible force, but rather follow the curves and distortions in spacetime created by the presence of other masses. One of the earliest and most dramatic confirmations of general relativity came in 1919. During a solar eclipse, astronomers observed starlight bending as it passed close to the sun, precisely as Einstein's theory predicted, cementing his fame. General relativity beautifully explained the long-standing anomaly in Mercury's orbit and predicted phenomena like gravitational lensing, where massive objects act like cosmic magnifiers, bending light from distant galaxies and distorting their images. So gravity, as taught by Einstein, is not a force in the traditional sense, but an inherent property of spacetime itself. It's the universe's way of telling matter how to move, and matter's way of telling spacetime how to curve, a profound cosmic choreography. Having understood gravity's fundamental nature, let's explore its immense power in action throughout the cosmos. From the largest structures to the smallest interactions, gravity is the master sculptor, ceaselessly shaping the universe. Perhaps the most familiar manifestation of gravity's power is in the formation of stars. Stars begin their lives as vast, sprawling clouds of interstellar gas and dust, floating aimlessly in the cold, dark vacuum of space. These nebulae, though immense, are incredibly tenuous. But within them, slight variations in density exist, tiny clumping regions where molecules are infinitesimally closer together than their surroundings. Gravity, even at these subtle scales, begins its work. The slightly denser regions exert a marginally stronger gravitational pull, attracting more gas and dust from their surroundings. It's a slow, painstaking process, but relentless. As more material accumulates, the gravitational pull intensifies, triggering a runaway collapse. The cloud begins to shrink, drawing in matter from an ever larger volume, becoming denser and hotter at its core. This collapsing core is known as a protostar. It's not yet a true star, as nuclear fusion hasn't begun, but it's a star in the making, steadily accumulating mass and building up immense internal pressure and temperature. For millions of years, gravity continues its relentless squeeze. The temperature and pressure at the protostar's core climb to unimaginable levels, reaching tens of millions of degrees Celsius. This is the critical threshold. Finally, the immense gravitational compression ignites thermonuclear fusion. Hydrogen atoms fuse to form helium, releasing an enormous burst of energy that pushes outward, counteracting gravity's inward pull. A star is born. This delicate balance between gravity's inward crush and the outward pressure from fusion is what defines a stable star like our Sun. They exist in a state of hydrostatic equilibrium, maintaining their immense size for billions of years. Gravity's influence extends beyond star formation to the creation of entire planetary systems. As a protostar forms, not all the surrounding gas and dust gets pulled into the star's core. Some material forms a flattened, rotating disk around it. Within this protoplanetary disk, gravity begins its next act of creation. Tiny dust grains, initially microscopic, collide and gently stick together due to electrostatic forces and weak gravitational attractions. Over vast spans of time, these small clumps grow into larger and larger aggregates, a process known as accretion. As they gain mass, their gravitational pull strengthens, allowing them to sweep up more surrounding material. This relentless accumulation eventually leads to the formation of planetesimals, rocky or icy bodies ranging from kilometers to hundreds of kilometers in size. These are the building blocks of planets. Planetesimals continue to collide and merge. their gravitational interactions become more significant, leading to a chaotic period of impacts and mergers, with larger bodies gravitationally dominating and sweeping up smaller ones. Those planetesimals fortunate enough to avoid catastrophic collisions and grow sufficiently large begin to clear their orbital paths, either absorbing or gravitationally ejecting other debris. This process forms protoplanets. The final stage is the formation of mature planets. The terrestrial planets, like Earth, consolidate their rocky cores, while the gas giants, like Jupiter, accrete vast amounts of gas and ice due to their enormous gravitational pull. Thus, from the initial wisps of gas and dust to fully formed, orbiting worlds, gravity is the sculptor, the architect, and the relentless force that brought order and structure to the chaotic early solar system. Beyond individual stars and planets, gravity truly reveals its cosmic scale in the formation and evolution of galaxies. Galaxies are colossal collections of stars, gas, dust, dark matter, and myriad celestial objects, all bound together. The universe began nearly 13.8 billion years ago with the Big Bang, a hot, dense state of pure energy. As the universe expanded and cooled, matter began to coalesce, driven by the ceaseless pull of gravity. Small fluctuations in the early universe's density provided the initial seeds for structure formation. Gravity exploited these tiny irregularities, drawing matter together into larger and larger clumps. These initial clumps grew into massive protogalaxies, drawing in more gas and dark matter from their surroundings. Over billions of years, these structures continued to grow through gravitational accretion and mergers. As protogalaxies accumulated more mass, the immense gravitational forces within them caused the gas and dust to collapse and flatten into rotating disks, where new generations of stars would be born. Gravity also dictates the shape of galaxies. Spiral galaxies, like our Milky Way, are characterized by their rotating disks and prominent spiral arms, formed by density waves sweeping through the stellar population. Elliptical galaxies, on the other hand, are typically older and often formed from multiple galactic mergers. Their stars move on more random, less organized orbits, reflecting a more relaxed gravitational state. Galactic mergers are profound gravitational events. When two galaxies approach each other, their mutual gravity distorts their shapes, triggering bursts of star formation and eventually leading to the formation of a single, larger galaxy. The Milky Way itself is on a collision course with its larger neighbor, the Andromeda Galaxy. Billions of years from now, gravity will inevitably orchestrate their grand, majestic merger, forming a new, larger elliptical galaxy. At the heart of most large galaxies lies a supermassive black hole, a region where gravity is so intense that nothing, not even light, can escape. These colossal objects play a critical role in galactic evolution. Gravity not only structures individual galaxies, but also orchestrates their arrangement on even grander scales. Galaxies are not randomly scattered throughout the universe, they are clumped together by gravity. These gravitational groupings form galaxy clusters, some of the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, vast quantities of hot gas, and immense amounts of dark matter. On scales even larger than galaxy clusters, gravity sculpts the universe into a vast, interconnected network known as the cosmic web. This resembles a colossal, three-dimensional spiderweb. The luminous filaments of the cosmic web are where galaxies and galaxy clusters are concentrated, drawn together by gravity into these vast, elongated structures. These are the highways of the universe. Between these filaments lie immense cosmic voids, vast regions of space almost entirely devoid of galaxies and matter, where gravity's influence has pulled matter away, leaving behind vast emptiness. This cosmic web is a direct consequence of gravity amplifying tiny density fluctuations present immediately after the Big Bang, pulling matter together over billions of years to form the universe's larger-scale structure. Gravity is also responsible for the cyclical ebb and flow of tides on Earth. This familiar phenomenon is not caused by the moon's direct pull on water, but by the differential gravitational force across our planet. The moon's gravity exerts a stronger pull on the side of Earth closest to it and a weaker pull on the far side. This difference in gravitational force stretches Earth slightly, including its oceans. This stretching creates bulges of water on both the side facing the moon and the side directly opposite it. As Earth rotates, different locations pass through these bulges, experiencing high tides. The sun also exerts a tidal force, though less significant than the moon's due to its greater distance. When the sun, moon, and Earth align during new and full moons, their combined gravity creates exceptionally high spring tides. Conversely, during quarter phases of the moon, when the sun and moon are at right angles to Earth, their gravitational pulls partially cancel each other out, resulting in weaker, neap tides. These tidal forces are not exclusive to Earth's oceans. They affect solid bodies too, albeit far less dramatically. Tidal forces are also crucial in the heating of moons like Jupiter's Io, making it the most volcanically active body in the solar system. Gravity's influence extends even beyond visible matter, hinting at the universe's profound mysteries. One of the most perplexing of these is dark matter, an enigmatic substance that doesn't interact with light or other electromagnetic forces. The existence of dark matter was first inferred by observing galaxies rotating much faster than could be explained by their visible matter alone. Their outer regions spun at speeds that should have flung stars into space. This discrepancy suggested that there must be additional, unseen mass providing extra gravitational pull, holding these rapidly rotating galaxies together. This invisible gravitational glue is what we call dark matter. While we cannot see dark matter, its gravitational effects are undeniable. It shapes the cosmic web, acting as a gravitational scaffold upon which visible matter aggregates to form galaxies and galaxy clusters. Dark matter makes up about 27% of the total mass energy content of the universe, dwarfing the ordinary matter that makes up stars, planets, and everything we can directly observe. It's truly the dominant form of matter. Then there is dark energy, an even more mysterious component. While gravity draws matter together, observations revealed that the universe's expansion is accelerating, pushing galaxies apart at an ever-increasing rate. This acceleration cannot be explained by gravity pulling things back together. It led scientists to propose the existence of dark energy, a pervasive, repulsive force inherent to the fabric of spacetime itself. Dark energy is now believed to constitute approximately 68% of the universe's total energy density, making it the most abundant component. Its influence effectively overpowers gravity on the largest cosmological scales. The interplay between gravity, dark matter, and dark energy determines the ultimate fate of the universe. Current models suggest a big freeze or heat death, where the universe continues to expand and cool indefinitely. While gravity is the primary force for structure formation, dark energy dictates the overall expansion, competing to shape the cosmic destiny. Their balance is a profound cosmic dance, one we are still striving to fully comprehend. One of the most extreme manifestations of gravity is the black hole. These cosmic enigmas are regions where matter has been compressed to an incomprehensibly dense state, creating a gravitational pull so immense that nothing, not even light, can escape. Black holes form from the remnants of massive stars at the end of their lives. When a star much larger than our Sun exhausts its nuclear fuel, the outward pressure from fusion can no longer counteract gravity's formidable inward crush. This leads to a catastrophic gravitational collapse, compressing the star's core into an infinitely dense point called a singularity. The star essentially disappears into its own self-made gravitational prison. The boundary beyond which escape is impossible is known as the event horizon. This is not a physical surface, but a point of no return. Crossing it means being inexorably drawn towards the singularity. There are different types of black holes. Stellar mass black holes, typically a few to tens of times the mass of our Sun, are formed from the collapse of individual massive stars. Supermassive black holes, found at the centers of most galaxies, range from millions to billions of times the Sun's mass. Their formation mechanism is still a subject of ongoing research, though likely involves accretion and mergers. Black holes don't just consume matter, they also profoundly influence their surroundings. As gas and dust spiral into a black hole's accretion disk, they heat up to extreme temperatures, emitting powerful X-rays and gamma rays. Some black holes also produce powerful jets of high-energy particles that blast outwards at nearly the speed of light, extending for thousands of light years. These jets can impact gas clouds and influence star formation. Contrary to popular belief, black holes do not suck everything into them indiscriminately. Their gravitational pull is only immense at very close distances. Far away, their gravity is no stronger than a star of equivalent mass. If our Sun were suddenly replaced by a black hole of the exact same mass, Earth would continue to orbit it just as it does the Sun, completely unaffected. The only difference would be the absence of light and heat. The extreme gravity near a black hole causes time to slow down, a phenomenon known as gravitational time dilation, as predicted by general relativity. An observer near a black hole would experience time passing slower than someone far away. Further pushing the boundaries of discovery, gravity reveals itself in the form of gravitational waves, ripples in the fabric of spacetime itself, generated by the acceleration of massive cosmic objects. These waves were predicted by Einstein's general relativity in 1916, but their direct detection remained elusive for nearly a century due to their incredibly tiny amplitude. The most powerful sources of gravitational waves are cataclysmic cosmic events, such as the merging of two black holes, the collision of neutron stars, or the explosive collapse of a massive star. When two black holes spiral closer and finally merge, they release an enormous burst of gravitational energy, far exceeding the energy output of all the stars in the observable universe combined, for a brief instant. In 2015, the LIGO and Virgo observatories made history, directly detecting gravitational waves for the first time. This monumental discovery opened a new window onto the universe, allowing us to hear the cosmos. The detected signal, a characteristic chirp, came from the merger of two black holes, one 36 times and the other 29 times the mass of our Sun. It was a precise match for Einstein's predictions. Gravitational wave astronomy allows us to observe phenomena that are otherwise invisible, providing unique insights into black holes, neutron stars, and the extreme physics of the early universe. It enables us to probe the most violent and energetic events in the cosmos without relying on light, allowing us to peer through obscuring dust and gas that would block traditional telescopes. Looking forward, the study of gravity continues to push the boundaries of scientific inquiry. One of the greatest challenges remaining is to reconcile general relativity with quantum mechanics. General relativity describes gravity on large cosmic scales, while quantum mechanics governs the universe at its smallest subatomic scales. They are currently incompatible, a major unresolved puzzle in physics. Developing a theory of quantum gravity, such as string theory or loop quantum gravity, is the holy grail of modern physics. It would provide a unified description of all fundamental forces, including gravity, across all scales. Such a theory could potentially explain the origins of the universe, the nature of black hole singularities, and resolve paradoxes at the intersection of extreme gravity and quantum effects. Experimental efforts are also advancing. Precise measurements of gravity on microscopic scales aim to find deviations from general relativity that might hint at new physics. Gravitational wave detectors are being upgraded, and new, more sensitive observatories, including space-based ones, are planned. These will unlock even deeper secrets of the gravitational universe. The ongoing search for dark matter particles in underground laboratories also exemplifies our quest to understand gravity's hidden components. If found, these particles would fundamentally alter our understanding of the universe. Beyond fundamental physics, gravity also plays a role in our potential future in space. Understanding orbital mechanics is crucial for space travel, launching satellites, and future deep space missions. The concept of artificial gravity in prolonged space missions, for instance, is a critical area of research to mitigate the health effects of weightlessness on astronauts. Even the design of spaceships and propulsion systems must account for gravitational effects, from optimizing trajectories to developing new drive systems that could manipulate spacetime itself. The universe, in its awe-inspiring complexity, is a grand testament to the power and elegance of gravity. It is the silent, pervasive force that weaves together the cosmic tapestry, from the smallest atoms to the largest structures. From igniting stars and sculpting planets to bending light and creating black holes, gravity's influence is inescapable and omnipresent. It's the ultimate architect, shaping the very existence of everything around us. Every moment of every day, we experience its pull, grounding us to our planet, yet its reach extends far beyond, holding galaxies together and guiding the very expansion of the cosmos. The journey to understand gravity has been a testament to human ingenuity, from Newton's groundbreaking insights to Einstein's revolutionary perspective, and the ongoing quest to unify all forces of nature. Each discovery, from the falling apple to the detection of gravitational waves, has deepened our appreciation for this fundamental force and its intricate role in the cosmic dance. As we continue to explore the universe, gravity remains our constant companion, a compelling mystery, and an indispensable tool for deciphering the universe's most profound secrets. The invisible hand of gravity ensures the celestial symphony plays on, eternally shaping the cosmos in ways both subtle and spectacularly grand. It is the silent force that orchestrates our universe. Let us delve deeper into how gravity, this omnipresent force, orchestrates the very balance of stellar life cycles, from birth to explosive death, and the formation of incredibly dense remnants. After a star forms and settles into its main sequence phase, like our Sun, it spends billions of years fusing hydrogen into helium in its core, maintaining a delicate hydrostatic equilibrium against gravity's crush. However, this fuel is finite. When the hydrogen in the core is depleted, gravity begins to gain the upper hand, causing the core to contract and heat up. For stars like our Sun, this contraction leads to the outer layers expanding dramatically, cooling and turning red, forming a red giant. This expansion is ironically a result of gravity's initial inward pull. In the red giant phase, the star sheds its outer layers into space, forming a beautiful planetary nebula. This leaves behind a small, incredibly dense core known as a white dwarf. A white dwarf is supported by electron degeneracy pressure, a quantum mechanical effect that prevents further gravitational collapse. It's a testament to gravity shaping matter into new, exotic forms. For truly massive stars, their end is far more dramatic. After exhausting their fuel, their cores undergo an even more catastrophic gravitational collapse, leading to a supernova explosion. This supernova is one of the most energetic events in the universe, briefly outshining entire galaxies. It scatters heavy elements, forged in the star's core, throughout space, enriching the cosmos for future generations of stars and planets. What remains after a supernova depends on the initial mass of the star. If the remnant core is between about 1.4 and 3 times the mass of the Sun, gravity takes over to form a neutron star. A neutron star is the crushed core of a massive star, so dense that a teaspoon of its matter would weigh billions of tons. It is supported not by electron degeneracy, but by neutron degeneracy pressure and even stronger quantum force. If the remnant core is more than about 3 times the mass of the Sun, even neutron degeneracy pressure cannot withstand the overwhelming gravitational force. The core collapses further, forming a black hole. Here, gravity utterly dominates, leading to the formation of a singularity and the event horizon, the ultimate cosmic prison, where mass is compressed to an unimaginable degree and spacetime itself folds in on itself. Thus, gravity dictates the life and death of stars and their spectacular end states. It is the force that takes diffuse gas and dust and transforms it, under immense pressure, into the dense, exotic objects we observe today. Consider the delicate balance that gravity maintains within our own solar system. Each planet is held in its precise orbit by the Sun's monumental gravitational pull, yet also exerts a tiny pull on the Sun and other planets. These subtle gravitational interactions between planets cause tiny perturbations in their orbits, which astronomers must meticulously calculate to ensure the accuracy of spacecraft trajectories. Gravity also allows for the practice of gravitational assists, or gravity slingshots, where spacecraft use the gravitational pull of a planet to gain speed and change direction, saving precious fuel and time. This ingenious technique dramatically expands the reach of our unmanned missions, enabling probes to journey to the outer solar system and even escape the Sun's gravitational influence into interstellar space. On Earth, gravity is an ever-present force, defining up and down, influencing weather patterns by pulling air masses and shaping geological features like mountains and valleys over vast timescales. The strength of Earth's gravity has also profoundly influenced the evolution of life. It determined the maximum size of land animals, the height of trees, and the very physiology of terrestrial organisms. Without gravity, there would be no atmosphere, no oceans, and no stable surface for life to emerge. It literally holds our world together and protects us from the harsh vacuum of space. Yet, gravity is not uniform across Earth's surface. Variations in underground density and topography create tiny local differences in its strength, detected by sensitive instruments like gravimeters. These subtle gravitational anomalies are used for geological surveys, helping to locate Chinese letter, and underground water sources, demonstrating gravity's practical application in resource exploration. Moreover, the ongoing expansion of the universe, driven by dark energy, continues to pose profound questions about gravity's ultimate fate. Will gravity eventually halt the expansion, or is the universe destined for infinite spread? Current observations overwhelmingly suggest an accelerating expansion, pointing towards the Big Freeze scenario, where gravity's pull is overcome, and galaxies eventually move beyond each other's cosmic horizon. This means that billions of years from now, future astronomers might only see their own galaxy, the remnants of our Milky Way and Andromeda merger, effectively isolated in a universe where other galaxies have receded beyond observability. Despite the ongoing puzzles, gravity remains the guiding principle behind countless cosmic phenomena and the bedrock of our understanding of the universe. It is both profound and profoundly practical. From the primordial soup of the Big Bang to the intricate dance of galaxies, from the birth of stars to the mysteries of black holes and gravitational waves, gravity is the invisible hand always at work. It sculpts and shapes, compresses and expands, brings together and tears apart, creating all the diversity and structure we observe throughout the unfathomable expanse of space and time. Our ongoing quest to unravel its deepest secrets, from quantum gravity to dark matter, represents humanity's continuous drive to comprehend the fundamental rules that govern our existence. The universe is still full of mysteries, and gravity, in all its forms, holds many of the keys. Each new observation and theoretical insight brings us closer to a complete cosmic narrative. So the next time an object falls to the ground or you gaze up at the moon, remember the silent, powerful force at play. Remember gravity, the invisible, omnipresent architect of our cosmos. It is the force that binds us to our planet, that holds stars in their fiery dance, and that dictates the grand evolution of galaxies across billions of light years. It is truly the invisible hand of the cosmos. And as long as there are minds to ponder and eyes to observe, humanity will continue to trace the intricate patterns woven by this fundamental force, forever awestruck by its beauty and its power.